Hey folks, how y'all doing? Um, just a reminder, I've got office hours tomorrow from 12 o'clock to 1 o'clock. I will be on Zoom no matter what. You can just drop in and station. I'll also be around from 6 to 8 tomorrow evening. This is by appointment. Let me know if you're coming. Otherwise, I'll use the time for something else. But if you have questions, I'll be around for that. I have couple of questions here that people have asked me over email to work in today's video. So let's go ahead and take a look at the first one here. Um, this was number 5 from exam 1. You have 28 identical coins. How many ways are there of distributing them among 3 children? Distributions do not have to be fair. Um, so there are a couple of ways that we can look at this. One way is to imagine sort of the problem that we did with the soda problem in the robots. Let's say that instead we had um, instead of having sodas, we had a robot here. A robot, and instead of having sodas, there are just tags with the names of kids. Um, and so that you know, let's just say the kids' names are A, B, and C. Um, we've got tags that read A, tags that read B, tags that read C, and the robot can grab as many of those tags as they want to, um, but has 28 spots in robot's box. Put these tags in, and then once the robot has picked out the tags, the robot will give 1 coin to each child for each tag that the robot has, and so then a correct order have 28 ones for picking a tag and 2 zeros. Um, one to try move from A to B, and then one from B to C. And so there would be 30 spots to fill, and we would have to pick 28 of them to do. Solution 30 choose 28, which is also the same as 30 choose 2. Okay. So that's one way of thinking about this is picking name tags out of an infinite supply of name tags to fill a box. Excuse me, that can hold up to 28 name tags, and then matching the name tags with coins. Um, Another way of thinking about this is sort of this way, that I have 28 coins lined up already. This is a different way of thinking about this. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 25, 26, 27, 28. Okay. And that gives us slots between each of these um, coins, as well as a slot before and a slot after. Okay. And so there are a total of, let's see, 29 slots here then. One before each of the 28 coins, and then one more. Okay. Um, and then there is, and what we're going to do is we're going to have um, put in these slots. We're going to put two flags. Um, so just a little flag here in one slot, and say a little flag here in one of the slots. And the flags will separate out the distribution so that everything before the first flag goes to the first kid, everything between the two flags goes to the second kid, and everything um, that comes after the second flag goes to the third kid. Um, and so, how many ways of doing that? Well, there are 29 ways of placing first flag. Let me think about this for a second. The trick is that because we can give a child 0 coins, we can put two flags in the same slot. Um, and so there are really it's like having an extra slot here. So let me back up here, explain what's going on here. So we have 28 coins. Um, we have 29 spaces where the flag can go. And so the first flag can go in any of the 29 spaces. So um, how many spaces are there now for the second flag? Well, the second flag can go in any of these 28 different spaces. Or to the left of the first flag or to the right of the first flag. So that this is now a space to the left of flag or to space to the right of flag here. So flag 2 has 30 spaces. And so that's 29 times 30. But the flags themselves are identical. And so rearranging the order of the two flags, if they are, say, especially if they're in different spaces, putting flag 1 here and flag 2 here is just like flag 2 here and flag 1 here. And so at the end, after we've counted all the cases where the order does matter, we divide by 2. And then that gives us a case where it doesn't matter. But that's the same thing as 30 choose 2, which is the same answer that we got before. We're placing two flags somewhere along this strip that tells us, where the divisions between the distributions occur. I think this approach is harder than the robot approach, but it does lead us to the same answer. Okay. I hope this helped with number 5, and I hope seeing two different ways of getting to that answer helped also. All right. Let's move on. Next question. This is the question about the ping pong balls. We want to construct a generating function that will allow us to work with this problem. 10 balls will be chosen from the drum, and the total number on the balls to equal 30. So we have two different values here that we want to look at here. So our two constraints. One is that the number of balls has to be 10. and one is the total of the value of them to equal 30. And I think this is pretty much the only way that satisfies both constraints is to have a term in the generating function for each ball. And end up having 10 terms. At and then each ball can have a total of 1 point on the ball up through 6 points on the ball. And so if we take this term here and raise it to the 10th power, my generating function will x first plus x squared plus x cubed plus x to the fourth plus x to the fifth plus x to the sixth raised to the 10th power. This guarantees that we're only going to have 10 balls. And then if I look at what's happened to the exponents smallest case I can have is where we pick 1 every single time, and that would give me x to the 10th. And the largest possibility would be we pick 6 every time. That would give me x to the 60th. Somewhere in there will be an x to the 30th term in there, and that's the term that will determine what. So we would multiply this out. We look for the coefficient in front of x to the 30th, and that would get the result that we. Okay. All right. So let's look at the next question here. All right. Sorry about that. Let's start with part A here. How many distinct permutations are there of the letters in this word? Okay. So that's not too hard. There are a total of 1 plus 4 plus 1 is 6, 7, 8, 9, 10, 11, 12, 13 letters. And so there would be 13 factorial different permutations if all 13 letters were different. But all 4 E's are the same. And so there are 4 factorial different ways of rearranging the E's that we can't tell them apart. And then there are 2 N's and 3 S's. And so this gives us the total number of ways of rearranging the. Okay. And so for part B, what we want to do is we want to exclude the cases that have 3 or more consecutive consonants. Okay. All right. So, what are the cases that do not contain 3 or more consecutive consonants? So there are a total of 8 consonants and 5 vowels. So if I look at the consonants for a second, there are 9 places where you can place vowels. You have to place them at least every, so that wow, this is going to be a lot of cases. Is there a fast way of doing this without having to break this down? A lot of cases. Okay, let's go ahead and dig in. 'Cause this looks like this could be a lot of cases. So what we want to exclude these combinations of um, arranging the consonants. We want to exclude a case where all eight of them are together, because that would be three or more, because there'd be eight of them that are together. We want to exclude the case where seven of them are together and then one of them is somewhere else. Six of them together and two of them are somewhere else, or six, one, and or five and three, five and two and one, five and one, four and four, four and three and one, four and two, four and four and two and two. Sorry, four and two and or I have to make another here. Four and one and one and one. Or three and five, and four and one, two and three and one, and two and two and one, and two and one and one, and finally three and one and one. I think those are all of the ways that we can break up eight where one of the factors has at least three or more consonants in it. Okay. All right. So then let's think about how we can do this. So what I'm going to imagine here is that we have just a single cluster of eight consonants. And so we have five vowels, four E's and one I. So we're going to place the five vowels here and then drop the eight consonants in someplace along here. Um, so there are 5 factorial divided by 4 factorial. There are 5 ways of arranging vowels. And then there are 8 factorial divided by 2 factorial and 3 factorial ways of arranging the consonants. Uh, and then those consonants can be inserted in one of 6 different places before the first vowel, after the first vowel, after the second vowel, after the third vowel, after the fourth vowel, after the fifth. So we've arranged the vowels, we've arranged the consonants, inserting the consonants in among. Okay. All right. Then 7 and 1, we are arranging the vowels, arranging the consonants. And then placing 7 of the consonants in one slot and 1 of the consonants in one of the other slots. And so that will be 6 places to put the first chunk, the 7 consonants, times 5 spots to place the. Okay. And then here we arrange the vowels, arrange the consonants. place a chunk of 6 consonants, and then we place a chunk of 2 consonants in slot. You don't want them in the same slot because that would be counting the placing all 8 in the chunk, same slot. That's why I've got 6 times 5. Okay. All right. So then all of these have the same sort of prefix here. This is the first one that has a repeated term, though. And so what we want to do is 6 ways of placing the 6. And then out of the other 5 slots, we want to choose just 2 of them. 5 choose the other 2 slots. And is that going to work? In the order for those. This, I think, is a terrible way of doing this, breaking that down into a whole bunch of cases and adding this up. But this would get us to the answer that we take the total number of cases and then subtract all of these cases that have 3 or more consecutive consonants. It might be easier to count the cases in what we do want. How would that work? We have 6 slots to place consonants among the 5 vowels. And we could place up to 2 at a time. So have the case where 2, 2, 2 somewhere among the slots, and then 2, 2, 2, 1, right? And then 2, 2. That would actually be fewer cases. So let's talk about this problem again. That's not an eraser, the eraser. So let's try this again. Is there an easy way to erase just all? Yeah, that can do that. All right. So, second approach. We have total of 5 vowels. Again, which means there are 6 slots here. Okay. I have to put 8 consonants in these slots, and I can't have 3 or more consonants. So I could put 0, 1, or 2 consonants here, 0 consonants here, 0, 1, or 2 consonants in spaces. Okay, so the possibilities are that I could put 2 consonants in 4 of these different spaces, or 2, 4, 6, 7, and 8, or 2, 4, 5, 6, 7, 8. But I can't go any smaller than this. I can't have this 2, 3, 4, 5, 6, 7, 8, because this takes a total of 1, 2, 3, 4, 5, 6, 7 slots, and there are only 6 slots available. So I can't do that. And so this gives me just 3 cases that we have to check out. Okay. So let's look at this again here. we're going to arrange 5 vowels. We're going to arrange the 8 consonants. And then we're going to choose 4 of these 6 slots for these pairs of vowels to go. So 6, choose 4. And then same thing here, arrange the vowels, arrange the consonants. And then choose out of the 6 slots, 3 slots that will take pairs, and then 2 more slots that will take singletons. So out of the 3 remaining slots, choose 2 of them. And then here, 5, 8 factorial over 3 factorial. Arrange the vowels and arrange the consonants. And then choose 2 spots out of the 6 to receive 2 consonants. And then out of the remaining 4 spots, you need to choose all 4 of them. You don't have to include that term. That's equal to 1. And those spots will each take 1. So if we add these numbers together, that will give us the number of permutations that contain consonants. Whole lot easier than figuring out what we have to exclude. I really botched that up the first time. Okay. I mean, I didn't botch it up. I just made it much more complicated than it had to be. But this, I think, is going to work better. All right. And let's move on. We got one more question to take a look at. This is off of question 2. In the game of Merrill's Cove, you can on each turn play a pair, a triple, or sequence, depending on the cards that are available in your hand. A pair scored is 2 points, or a triple scores 3 points, and a sequence. Right. N represents a number of points, and an A with a little n is the number of ways. Scoring. We want to write a recurrence relation for the sequence A sub n. Okay. So let's say we have want to score n points. This can happen in A sub n different ways. Some of those ways will start with a P, start with a pair. But if we start with a pair, then what's left is to score n minus 2 points. And if A sub n is the number of ways of scoring n points, then A sub n minus 2 is the number of ways of scoring n minus 2 points. That's if I start with a P. Then this is the number of points left to score, so this would be the number of ways of scoring. Or I could start with a T, in which case I would have n minus 3 points to finish the game. And that can happen in A sub n minus 3 different ways. Or I could start with an S, and that would also be n minus 3 points. And A sub n minus 3 different ways. Ooh, all right. Well, these are disjoint cases because they all start with a different letter. And the rule for disjoint cases is we can use the addition rule to get a total. And so A sub n breaks up into A sub n minus 2 plus 2 times A sub n minus 3. and that finishes up 8. Okay. All right. If you have other questions, send them by email, and I will be happy to record a second video on Wednesday to incorporate some of your answers. All right. Y'all take care.